probably mostly talk about boundaries. I don't think I'll get around to perturbations. Maybe I'll say a drop. But the basic message that I will try to get across in this talk is that there's a nice interplay between integrable structures, so things like McDonald processes or vertex models, also matrix product ansatz, and probabilistic techniques, and that by combining these two, you can gain some knowledge about physical phenomena that you would not really get from either alone. The physical phenomena that I'll focus on primarily is understanding, as roughly the theme of this workshop, the stationary measures or invariant measures. But I'll be looking at a stochastic system with boundaries. So I'll talk about the KPZ equation. I'll also talk about the log gamma polymer in the spirit of what Neil was talking about. You know, the overarching message is that by introducing boundaries, you make the nature of invariant measures much more interesting. And there's still quite a lot to be understood there. So let me kind of give you a preview. This is, in a sense, what I won't talk about, but I'll use this as the motivation for what I will talk about. I won't talk about, except for this one little bit, the KPZ equation on a finite interval. I will mostly focus in the half space, but let me speak a little bit about the finite interval. So the first kind of disclaimer is, you know, box ball systems are very discrete objects. The KPZ equation is a very continuous object. Don't worry if that doesn't make so much sense to you. A little bit later, I'll talk about a more discrete object. I won't go to the most discrete, which would be a vertex model, but I will go to the level of a discrete polymer model. But bear with me if you can about the KPZ equation. So this is a model for stochastic interface growth. The idea, which is kind of illustrated on the left, is that pointer. You have some interface, some rough interface, and you denote this by h. T is time, x is the one-dimensional space variable. And I'll assume I'm on some finite interval, say 0, 1, or 0. And over time, it will grow or shrink according to this stochastic PDE. There's a Laplacian, which is a smoothing mechanism, a nonlinearity, which somehow is going to say that depending on the local slope, you might have a different rate of growth. And then the very important space-time forcing. So what this really means is there's some smoothing, there's some roughening, and then there's some stochastic forcing. And we'd like to understand how it behaves. Of course, when you put yourself in a finite interval, you need to impose boundary conditions. When you're on an infinite interval, you can get away without it, or you can put yourself in a periodic domain. On a finite interval, there are various natural choices for the boundary conditions. You know, one could be that you pin the height at the left and the right to be certain values. That actually turns out to be easier than if you allow the height to vary, but with essentially a fixed slope at the two boundaries. And that's what we'll focus on. Now you can ask why fix the slopes and not the height itself? Well, there are a few different perspectives as to why, right? One could be that somehow you have a substrate and a boundary, and they interact in a certain way that actually enforces that. So you see this with things like sand, you know, the way sand piles at certain angles. You know, the other perspective is that if you actually take the derivative of this, the spatial derivative, what you get is something called the stochastic Burger's equation. And so the stochastic Burger's equation is a continuum polymer. It's a continuum version of interacting particle system. And then these boundary conditions actually become conditions on potentials, that you have certain rates at which particles get fed in on the left and on the right and taken out on the left and the right. And so this is actually, the derivative is some sort of continuum version of something like the asymmetric simple exclusion process with these open boundary conditions. So this is a very natural model to study. But, you know, what are the natural questions? Well, you know, oftentimes the first question you'll ask is about the invariant measure. And if you think about this model for a little while, you'll realize there is no invariant measure, at least no invariant probability measure. Because what will happen is the entire height function will just drift away. Right? In the same way that if you just take a random walk and you asked what is its invariant probability measure, there would be none because it just kind of runs away and diffuses. So the right thing to look at is not the absolute height function itself, but rather the increments of it, or really the stochastic Burger's equation. So you look you look at the height relative to the value at position 0, and you ask, how does that behave? And now you've kind of compactified things, because you can't have this running away. So the question is, what happens as time progresses? Does this converge to some unique invariant measure? And can we describe what that unique invariant measure is? Okay, there's a question mark on this arrow, and what I mean by that is that we don't know how to prove, or well, we haven't proved yet that as time goes to infinity, you converge to what I'm going to show you on the right-hand side. But what I will show you is nevertheless provably an invariant measure for this height increment process. And what it is what can be termed a boundary one-dimensional Liouville quantum gravity measure. And I'll describe it, and then we'll see a discrete version or some variant of this a little bit later in the talk. So first of all, I'm going to assume that these boundary parameters, u and v, are, well, they sum to be bigger than 0. And I'll say that there are some issues when you don't assume that, and I'll explain them in a moment. Now, what that really means is that the slope at the left side of this increment is somehow positive. Well, okay, there's some balance between these two slopes. I've enforced the slope as being minus v on the right and plus v on the right, on the left. In terms of the invariant measure, what you find is the following. So first of all, you define the following infinite measure. So you take Lebesgue measure at the starting point. Okay? And then away from that, you choose a Brownian motion. Okay, so I'll call this a free Brownian motion. Infinite's not a probability measure. Now I reweight that measure, that infinite measure, by a Radon-Nikodym derivative. And by doing this, assuming it's normalizable, I will define a probability measure. In the same way that you take Lebesgue measure, you multiply by a Gaussian, you reweight it, you get a Gaussian, which is a probability measure. So what is the Radon-Nikodym derivative? It's of the form e to the minus n energy. And the energy has 3 components. So it has a boundary linear component, okay, that is dependent on the height of that free Brownian motion at 0 multiplied by u. You have another boundary at the right-hand side that has a linear component with the factor v. And then in between, you have an exponential energy that you integrate from 0 to 1. If you just had this exponential inside, this is this Liouville quantum gravity measure, but here you impose these boundary conditions. Now, if you assume that u and v add to be positive, or for the moment, let's assume that they're both positive, just for simplicity. So if they're both positive, you see that the potential is really pushing you up at the boundaries. You want to have you want this to be as high as possible on these 2 boundaries, and you want this in the middle to be as low as possible. This is how you will, really maximize your probability. And it turns out that these 2 things balance sufficiently so that then this Radon-Nikodym derivative integrated over this infinite measure, this free Brownian motion measure, is normalized finite. So you can define a probability measure. And then the increments of this path under this probability measure are invariant for this KPZ equation on it. Yes, that's a non-trivial result. I don't know a direct way to verify it, because, well, you would need to write down the generator of this equation. That's not an easy thing to do. And then you would somehow need to show that the generator acts gives you 0 on that. I don't know how to do it. So the approach that we take is different. It's well, you go through a discrete model, some pre-limiting model for which you can show that that you have an invariant measure, and then you show that the model converges to this, and that the invariant measure converges to the invariant measure here. And with a little bit of tightness, a little bit of details, you can prove that that will imply that the limit is in fact invariant measure. Okay, so this is I'm not doing this story, but I'm going to just tell you that the route that we took, so this result is a culmination of quite a number of years of different works, but this story really begins with the work of Derrida, Evans, Hakim, and Pasquier and the matrix product ansatz. And this is for the asymmetric simple exclusion process, the open boundary version. And then, there are various routes that you can take. In fact, there's a different route that doesn't go through Askew-Wilson processes, but that's only been developed recently. But there's anyway, you find different representations for this matrix product ansatz, some which are better for asymptotics than others. And ultimately, you then connect ASAP through a weak asymmetry scaling to the KPZ equation, and you take a limit of the Askew-Wilson process formulas from this matrix product ansatz, and so forth. This eventually brings you to the form that I've given. So it's a rather indirect route. That's a long story, indirect route. So what I'm going to kind of advertise as the purpose of today's talk is to explain to you a much simpler and much more direct route. And I'll explain it in the context of the half space model. Okay? So I don't yet know how to do this in the bounded interval. but it will answer the following question, which is, why does the stationary measure look like a polymer? In other words, why does the stationary measure itself have this description as a path integral against a Brownian motion involving a potential? And if you paid attention to Neil's talk, you actually would, you see this exponential form. This is exactly the same type of form that he had in the quantum Toda Hamilton. And that's not coincidental. In fact, this is because what we're seeing here is somehow related to a two-level polymer in the spirit of what he was talking about. And I'll try to elucidate exactly how that works. Okay, so that's the goal of the talk, is to really explain where this somewhat cryptic result comes from without going through this picture. And so what I'll do is I'll focus now on the related half-space model. I'll tell you a little bit about the phenomena associated with the model, and then I'll give you a proof of the invariant measure. And the proof will go in the following way. I'll talk about a discrete model, the log gamma polymer in a half space. I'll tell you two properties of it. Well, really just one property. One property has to do with a certain symmetry, and that comes from integrability. And then I'll give you a very simple path argument that will prove the invariant measure. And you'll see from that exactly why you get these sort of two-level polymer. KPZ on a half space, exactly what you would expect. You take the KPZ on a bounded interval, you take one interval to infinity. So now you only have one boundary condition at 0. Okay. Now, of course, since you've taken the other boundary to infinity, there might be some interesting things. How does stuff at infinity affect what you see around 0? Right? And we'll see that, in fact, in the sense that there's a very interesting phase diagram associated to this equation. I should say, just backing up very briefly, in this case, I put this question mark. So what the question mark really means is there's a conjecture that for any choice of u and v, you have a unique invariant measure, and you have ergodicity, so everything will converge to that. In the half space, it turns out the picture is more complicated than that, and I'll explain that. So again, the question here is, what does the long time solution look like? Or in other words, what are the invariant measures, and how does what invariant measure you arrive at depend on the initial data? And so here's the conjecture. So here's the conjectural phase diagram, and I'm going to spend a little bit of time explaining. Consider an initial data for your half space equation that has some decay or growth condition at infinity. It has some limiting slope. Now, obviously, you could create things that don't have a limiting slope, and I don't quite know what will happen there. But assuming that you have some limiting slope at infinity, you might think that that slope somehow is enforcing a potential. It's somehow enforcing a boundary condition at infinity. And you want to know, how does that translate back into the invariant measure you see? I mean, obviously, it won't necessarily start with an invariant. So the claim is that then the increment process, so if you look at htx minus ht0 as a process in x, okay, so really you focus around what's happening near the boundary, right? That's the topology you should have in mind. Then the claim, obviously conjecture, is that as time goes to infinity, the invariant measures that you arrive at are given by this diagram. And the first thing that I want to emphasize is there are 3 regions to the diagram. And in 2 of the regions, there's non-uniqueness, in the sense that different slopes v will bring you to the same invariant measure. So first, let's look at this left. The type of invariant, the type of initial data that you should imagine arises here. This is the UV axis. Is that around 0 you have some slope, okay? And in fact, the slope should be negative because u is less than 0. And then the slope eventually gets worse, more negative. That's the type of initial data. And the claim is that if you have that type of initial data, what the terminal slope is doesn't end up mattering at all in terms of the invariant measure. Basically, the slope near 0 will win. And in fact, the limit will be a Brownian motion, only depending on this u. So in other words, having this drift u. Okay, so in other words, for each value of u, the entire line that goes from this u equals v all the way up to infinity, the same invariant measures will arise in those. Now, the other region of non-uniqueness is when u and v are both positive. So in this case, the picture to have in mind is, so u being positive means you have a positive slope here, and v being positive, well, remember, this is a minus v, means that you have a negative slope over here. So in other words, you still have this situation where the slope at infinity is negative, the slope near 0 is positive, and somehow the effect of that moves away. So things start to kind of flatten out or see the behavior of u, but they forget the behavior of the v. Now, most interesting is the case when u and v lie here. So u, whatever this region corresponds to, the picture is the following. So the slope around 0 is less than the slope at infinity. And the claim is that the slope at infinity will now hold the system up sufficiently so that it actually stays in the picture. So this is the one condition under which the slope at infinity will maintain its effect. Now, I haven't told you what this HU0 or HUV is, and I will in just a moment. But let me tell you at least why this is a reasonable phase diagram. Okay? And this is not a proof of it. But you can get a sense as to why this might be a reasonable phase diagram, at least that you might have these effects from the Feynman-Katz interpretation for what the KPZ, solving the KPZ equation means. So what I mean by this is that if you take the KPZ equation, there's this transformation, which is just to say you exponentiate it, and you see that that solves the stochastic heat equation. Now, once you recognize that, then you can write a Feynman-Katz representation for this multiplicative noise stochastic heat equation. And what's written here is essentially that, except that we're in the context of the boundary condition. So the underlying path measure needs to be, relative to that boundary condition. So what you get is the following picture, and they're the quotation marks because there's a little bit of work to make sense of this, but it's at least heuristically true. That HTX is the log of the expectation under a certain type of Brownian measure of the exponential of two terms, one which samples the initial data at the point B0. So you have a Brownian motion that moves from position X at time t backwards. Now, because it's on a half space, it actually has an interaction at 0, which is either attractive or repulsive, depending on the sign of u. And then you sample the initial data, plus you also sample the noise along the path. And this gives you an energy, and you take the expectation of the exponential of this overall path, and this is the Feynman-Katz representation. Now, the point is that when u is negative, this represents an attractive interaction at 0. In other words, the Brownian motion gets rewarded for going near 0, probabilistically. And if u is positive, it gets repulsed, it gets penalized for going near 0. So now if we look back at our phase diagram, we can at least start to understand why we get these different phases. So this first term, this H0B of 0, this says that if the slope at infinity is quite negative, you're heavily penalized for your Brownian motion going far away from 0. Right? Brownian motions like to spread out, but if you end up too far, you end up in a very negative region, and you get penalized probabilistically. There has a very small contribution to this. So what that would mean is that in this sort of situation here, your Brownian motion rather wants to sample initial data around 0. And that's why the behavior at infinity is forgotten. And there's a similar sort of effect going on in this region on the top. Now, in the bottom where you have the HUV arising, it's because you have this positive slope at infinity, it balances with the fact that you also have some interaction at 0. And so there's the growth at infinity and the behavior of the Brownian motion around 0 balance, and you get this non-trivial invariant measure coming up in the way. So of course, none of this is proving, or none of this is even deriving the nature of it. It's simply telling you it may be a reasonable phase diagram. Okay. So this is the point. Let me remark kind of historically, this phase diagram has come up in a few different contexts. So one, probably the earliest I know of, is Tom Liggett's work on asymmetric simple exclusion process in a half space. So there, he also arrives at a phase diagram that basically says that if you have a boundary interaction in this ASEP, and you have a certain density at infinity, depending on these two parameters, you have different types of invariant measures. He doesn't give the invariant measure, he doesn't give formulas for them, but he says, that you have uniqueness of the types of invariant measures that arise. And it's the same phase diagram. The other context is actually, if you take the formulas for open ASEP, the boundary, you can actually identify them with something that was studied by Haria and Yor, same Yor from Neil's talk, about 20 years ago. And in their work, they were interested in certain exponential functionals of Brownian motion, and in particular, taking the limit as one boundary went to infinity. And when you look at the invariant measures, these formulas in finite interval, and you take one of them to infinity, depending on the parameters u and v, you will arrive at the same phase diagram. So in a sense, they studied this, not being motivated at all by the KPZ equation, but they studied the limits of these sort of invariant measures, these 1D boundary Liouville quantum graph invariant measures. Okay, so I'm not going to prove the conjecture in the sense that I'm not going to prove that as t goes to infinity, these are the things you get. But what I will do is I will tell you exactly what these h's are, and then I will prove to you that they are themselves invariant. Okay, so what are these processes? So B sub u is just simply a drift B Brownian a drift U Brownian motion. So that's, I already told you. Now the interesting case is so when u is real and v is less than the minimum of 0 in u, and if you check, what this corresponds to is exactly this bottom region. Okay, because what's happening here is that whatever happens on this boundary on the x-axis gets propagated all the way up vertically. So the claim is, in fact, that the only, or at least the extremal invariant measures for this half-space KPZ equation are exactly the ones that arise in this domain. And what I'm going to give you should be all of them. Okay, so under this condition, the HUV of x takes the following form. So it's written in terms of two independent plus or minus v drift Brownian motions. Okay, so I'm assuming, I guess, that v is negative. So these are independent. There's two different ones, even though, okay. So and then there's an auxiliary random variable which is inverse gamma distributed with parameters u minus v, and you can check that u minus v is positive. So the invariant measure takes the following form. So you have a drift v Brownian motion, and then you have the logarithm of 1 plus the inverse of this inverse gamma. So I guess I could have just written it as a gamma. And then the integral from 0 to t of the difference of the negative drift Brownian motion and the positive. Now, again, if you remember from Neil's talk, this is exactly like the two-layer O'Connell-Yor or semi-discrete polymer, in the sense that you have these two Brownian motions, and at some point you jump between them and you're looking at these increments. And you could write it even more in that form as well. So the claim is that this is invariant, and this is actually a process that had been previously studied by Harry and Yor, completely different motivation. So again, why is this invariant, and why does this look at all like a semi-discrete polymer? This is what I want to answer. Okay, so to answer this, I will now move to a discrete model, or more discrete model. So if you got lost on the KPZ equation, you come back, and I'll tell you something very concrete. Nothing continuous. Well, okay, the random variables are continuous, but that's okay. So the model that I'll study is called the half-space log gamma polymer. And I'll just tell you from the start that this is some discretization or semi-discretization of the KPZ equation. And I'll tell you exactly how in a little while, but just bear that in mind. All right, so this is a model which is defined in the following way. So you have an octant. I guess we assume that the bottom point is 1, 1 for some reason. And you have a bunch of parameters, alpha naught, alpha 1, alpha 2, alpha 3, so on and so forth. And what these alphas correspond to are parameters that define random weights, random variables that I will put at the vertices of this octant. Okay, so these are the red dots. So each one of these, at each of these red dots, I choose an independent random variable with a very specific distribution. And the distribution is that on the diagonal, they're distributed as the inverse, so 1 over a gamma random variable with parameter alpha naught plus alpha I. And in the bulk, so away from the diagonal, they're alpha I plus alpha j are the parameters. Now, of course, you could have taken all of them to be the same, and that's fine. But there's a lot of value in introducing these inhomogeneities. This is a common thing, for instance, in quantum integrable systems, to use these inhomogeneities to your advantage. And we will see that play out very clearly right now. No, the only condition is that all of these sums should be positive. Okay, so what do you do with all of these random variables is you form a partition function. Okay? Now, of course, There's more that you can do. You can define a polymer measure, and you can study its properties. I'll just focus on the partition function. The partition function is a sum over all upright paths in the octant of the product of the weights that you encounter along that path. Now, this should actually remind you of this sort of Feynman-Katz type stuff I was telling you from before. This is exactly some discrete version of that Feynman-Katz representation for the KPZ equation, up to the fact that I didn't take the logarithm here. So again, I sum over paths. So this orange is representing one such path. I need to determine my endpoint. So I end at xy. I start at 1, 1. And then I take the product of the weights that I encounter. Now, of course, each product is a product of IID, or not IID, of independent random variables. But when I take a sum over it, I get a rather complicated random variable. Now, of course, you can see either from this fact that this is some discrete version of that Feynman-Katz representation, or from the fact that there's a nice recursion relation for this partition function that's a version of the stochastic heat equation. Either way, you can see that somehow this should be functioning at the level of the exponential of the KPZ equation. In other words, if I take the logarithm of z, that should represent a sort of discrete height function. And moreover, if I take the difference of the logarithms, or the log of the ratio of partition function, that should function like the stochastic Burger's equation. In other words, that should be like occupation variables for a particle system. So that's the thing that I will search for an invariant measure for, really the ratio or the log of the ratio of partition. Now, here's the only integrable fact I will tell you about this model. And this is the thing that makes this model special. If I look at the law of the partition function along a given row, so I go up to height y, and I look at the random variables, which are these partition functions as I march across horizontally. Jointly, this law, which depends only on the parameter, on the alpha parameters, right? Because that's the thing that determines the weight. This law is invariant under permuting the first y of these alphas, alpha 1 through alpha y. Not at all obvious. And I'll tell you what it does not say. It doesn't say that you can permute the rows or the columns or anything of that sort and get the same partition function on the same probability space. This is purely a statement about the distribution. So it says that the distribution. So for instance, if I just look at, z y, this tells me that that distribution is invariant. That's a one variable thing. I can draw its distribution. I think of it as a function of the alphas. It's invariant under the action of the symmetric group on alpha 1 through alpha y. Now, of course, if I switch alpha 1 and alpha y plus 4, it won't be invariant. But I within that first y, this is true. Now, okay, I'm not going to prove this for you. I'm sorry. I'll tell you where it comes from, though. So it comes from, well, there are different ways of seeing it. So the way that the way that I immediately see it is that this half-space model is related to something called the half-space Whittaker process. So there's a way of embedding these partition functions in a measure on kind of continuum limits of partitions, in the sense of Young diagrams, and those measures that get written in terms of things called Whittaker functions, actually things Neil mentioned, you can see the symmetry exactly from the symmetry of Whittaker functions with respect to its parameters. Now that might not be the most fulfilling answer, but that's what I'll give. There are other approaches to see this. You could try to prove it directly. I don't have a proof of that. Another proof route, which has not been done but should be doable, is through the Yang-Baxter equation. So you can use the Yang-Baxter equation, at least in the full space setting, to prove symmetries of models with respect to the parameters. And I expect that one needs to work with the boundary K matrices and fusion and things like that. That has not really been done, but I expect that this symmetry would come from that as well. These are these are inhomogeneous. And so this one fact will give us the invariant measure. And so that's what I want to explain to you now. How, accepting this fact, do you get the invariant? Why is it called log gamma? Or what is this gamma inverse? Oh, you mean what is the term law? Oh, it just means the distribution. So the law of a random variable is the distribution that the random variable follows. You mean, what is that distribution? I don't remember. It's, you know, a gamma random variable, the density is written in terms of the integrand for the gamma function, right? It's a generalization of the exponential random variable. So the inverse is just defined as 1 over a random variable that has that distribution. You can write down the density. It's a very compact form of the same flavor, involving, you know, the minus 1 over x or something like that. But you're not going to see this result from that immediately. So that's why I'm not going to. Okay. So how do I use this invariance, which you'll believe me on, in order to construct the invariant measures? Okay, so here's my claim. So I claim this is a corollary, and we'll see why. I'm going to choose the parameters of my half-space log gamma polymer very carefully in such a way as to create sort of a renewal point that using the symmetry, I can actually move up arbitrarily, and that will create my invariant. So this is the basic idea. So let me talk you through it. So what I'm going to do is I'm going to choose my parameters so that on the diagonal, my alpha naught, I'm going to set to be u. Okay, so I should have these two parameters, u and v, but actually I'll have another parameter, alpha, because, you know, the model needs some bulk weights. It needs weights in the middle, and u and v are the boundary. Alpha is going to be the bulk weights. So what I'll do is I'll choose u naught to be u, or sorry, alpha naught to be u, alpha 1 to be v, alpha 2 to be minus v, and something weird is going to happen because of this. And then all the other alphas will be the same. So they'll really just be kind of 2 or maybe 3 non-trivial parameters. Now, what will happen, I claim, and of course, there are some conditions I need to impose for this to make sense, is that the law of the ratios, I could put a log in, but it makes no difference for the statement. The ratios of the partition function at position y plus k comma y divided by the partition function at y. I claim that as a process in k, this distribution, this law, is independent of y. So in other words, I go up to height 2, and I look at z2 divided by, you know, z22 divided by z22. Well, that's easy. That's just 1. I look at z32 divided by z22, z42 divided by z22, so on and so forth. That's a bunch of random variables. The distribution of that is the same as if y had been 17, not 2. And that's the claim. Okay. Now, what is it that these parameters do to the model? So first of all, the easy thing is that if you look at a position which is kind of far into the bulk, you know, where I and j are both bigger than 2, for instance, you see that you just have kind of IID random variables, gamma inverse of 2 alpha, right? So you have alpha I plus alpha j, and alpha I and alpha j are both alpha, and so they sum to 2 alpha. So this is somehow representing in the KPZ equation, this is the white noise that sits in the bulk of the model. Now on the boundary, on the upper boundary, we have a bunch of u plus alpha random variables. And these are going to represent the boundary conditions that are enforced, this Neumann boundary condition with parameter u. Now, obviously, it's a little bit more complicated here, but it's still the same idea. And similarly, along the bottom right, you get these gamma inverse of alpha plus v, and this will represent, in fact, the behavior at infinity, because this will say that if you go really, really far out, you'll see some drift. Now, the interesting things are around here. So you have at position 1, 1, you have a gamma inverse of u plus v. Now, if I assume u plus v is positive, this is a random variable that makes perfect sense. But in fact, I don't need to assume u and v sum to something positive, because this random variable is common to both the numerator and the denominator. In other words, all polymers need to originate at position 1, 1. So when I take the ratio of the partition function, that term just drops out. And so in fact, I can work beyond this condition of u plus v being positive. And I had mentioned in the beginning that there's this issue with this boundary Liouville quantum gravity stuff, that if u plus v is negative, it doesn't really make sense. The different potentials don't balance. And in fact, there's conjectures, but we don't know how to prove for the finite boundary case what is the invariant measure there. In this case, because you can factor out this divergence, we actually get it for the full parameter space. Okay, so this is an important point. Now, the other important point is that because alpha 1 plus alpha 2 I've tuned to be 0, you get a gamma inverse with parameter 0 at position 2, 1. Now, you should really think of that as just being a big infinity sitting there. Okay. Now, if you prefer, you let v minus, you tune these so that it's not v minus v, it's like v minus v plus epsilon or something. You take epsilon to 0. The point is that this puts an infinity into all of your partition functions. Now, again, this actually isn't an issue ever, because all partition functions, they involve paths, but the paths always need to take one step to the right initially, right? Right, because otherwise they would exit the octant. So every single partition function, you can factor out both the thing at 1, 1 and the thing at 2, 1. So this divergence doesn't even factor in to this ratio. So this is a well-defined ratio, is my point. And you see that this ratio when y is equal to 2 then depends on 3 things. It depends on the variable at position 2, 2, so some inverse gamma, and then these sort of geometric random walks that involve these 2 different sequences of inverse gamma random variables. And in fact, so the y equals 2 case of these partition ratios can really be written in terms of a 2-level polymer. Now, the non-trivial content is the fact that if I increase y, this thing will stay the same. And so let me prove this for you. So I'm going to use the symmetry. So the symmetry proceeds as follows. I take alpha 1 and alpha 2, and I'm just going to lift them up and swap them with alpha y minus 1 and alpha y. Now, when I do this, I don't change the distribution of the random variables. So I don't change the distribution of the ratios. We know this. On the other hand, if I look at the ratio of the partition function now at level y, I see that, okay, there are 2 types of partition functions at level y. There are 2 terms that will contribute to the partition function, right? It's a sum over all paths. So I can take that and I can split it up into the sum of all paths that cross through this orange point and the sum over all paths that don't cross through, right? So some of my paths will cross, some of them won't. Now, the paths that cross there will get rewarded with an extra infinity factor or some diverging factor. And some that doesn't will just stay finite. So when I look at the ratio of partition functions, I have something of the form infinity times the partition functions that go through that point plus something finite divided by infinity times the partition functions that go through that point plus something finite for 2 different endpoints. So because of that, L'Hopital's rule tells you that it should just be equal to the ratio of partition functions that go through this point. Now, partition functions have, when you condition them to go through a point, factorize, right? Because the sum over all paths that go from A to B, then go through C, factors into A to C times C to B. And so since all of the partition functions will then share the same factor corresponding to this bottom corner, my ratio, the thing I was interested in here, actually only ends up depending on the top 2 rows. But that was exactly back to the y equals 2 case. So this proves the invariance. And so to finish the story here, all that you're left with is to relate this half-space model to the half-space KPZ equation. And there is work to be done there. There's work going back to Albert, Skahan, and Pastel that does this in full space. And obviously, you need to work to do this in a half space as well. But the same will go through, and you get this discrete analog. Okay, so let me just see. I have until 2. Okay, so that was what I wanted to tell you about the invariant measures. And I should say that there are many other questions to study here. So, for instance, proving this ergodicity, proving the behavior on for U plus V negative of the finite model, extending this sort of picture to vertex models. And actually, I asked Makiko about the question of whether in the context of box ball systems, right? You have these model. There's this phenomena where for stochastic vertex models, which all of this is somehow a limit of, a lot of the invariant measures that arise there also are invariant measures for box ball systems. And so a natural question is, what about in this sort of half-space setting? So of course, in terms of the vertex models, this would mean doing it in an octant, or in terms of the box wall system, you would study the model in an octant with some carrier boundary conditions and some initial boundary conditions on the integers, on positive integers. And so really the question that I have is, does the structure of the invariant measures that we're seeing here, which is this non-trivial sort of path integral type structure, or matrix product onset type structure, does that also persist to box ball systems in this sort of octant, half space type setting, or for that matter in a diagonal strip where you have two boundary. Okay, so the other thing I wanted to talk about, but maybe I won't say much about, is the behavior of second class particles in ASAP. In particular, the construction of something called the ASAP speed process. The only thing, so let me, without any pictures, let me just tell you what that story is, and then obviously I'm not going to have time to talk about it. But the idea there, and in fact it's very related to these multi-species particle systems and invariant measures, but is that you're interested in a setting. Let me show you the picture. So you're interested in a particle system where you have different colors or classes or species, whatever you want to call it. And the rule is that lower classes are better than higher classes. So it's like on an airplane. It's not like in society. So first class, forces second class to do what they want. So the rule is that usually particles in ASAP will jump left or right with rate L or R. And so if you have a high class particle, it jumps right at rate R. And if there's a lower class next to it, it forces it to switch. So in other words, you swap low class and high class in some asymmetric way. And so I less than J turns to J bigger than, well, okay, the two flip their positions at rate R, and they flip the other way at rate L. And I assume R and L are different. Now, what you can do from this is you can actually create what's called a rainbow type initial data, which is that you actually say that at position I, initially, you have a particle of class I. Okay, so the further you get to minus infinity, the better the particles, the business class, Polaris class, whatever the different rankings are. And then this has the property that if you just project, you can lump together, you can say the particle at the origin had class 2, everyone to the left has some better class than it, but from the perspective of the second class particle, doesn't know the difference between them. They're all just better than him. And everyone to the right is all just worse than him. So it's basically the perspective of one particle is that you start with a bunch of lower class particles to one side and a bunch of higher class particles to the other. So step initial data and a single second class particle. And so the question, which has been studied for some time, is to understand the limit of the behavior of this second class particle. Now, usual hydrodynamics would tell you that if you just looked at the first particle in a usual one class system, particles and poles, the first particle would kind of run at the edge of the rarefaction fan. But the second class particle gets kind of bullied around by the first class particles, pushed left, pushed right, so on and so forth. And what turns out to happen is that he actually chooses a uniform distribution in the rarefaction fan, in this hydrodynamic rarefaction fan. And not only does he choose a random direction, he actually chooses it and then sticks with it. So the theorem is that if you look at this location of the second class particle as a function of time, you divide by t, then a limit exists almost surely. In other words, what you're seeing in this picture, I think this is just a bunch of samples from you repeat the experiment with lots of different systems. You see that each one of these lines is somehow filling out this rarefaction fan, but each one is essentially linear. The second class particles really go in this linear direction. And so because of this, you can define a limit speed for each of these particles. So the particle that started up at position I, if you look at its location at time t divided by t, that will converge to some limiting velocity. And you can do the same thing for I+1 and I-1 in this infinite colored system. And I don't think I'm giving the picture here, but anyway, you get something called the ASAP speed process, which has very interesting properties related to these multi-species or these colored invariant measures. And it basically has the property that there are convoys of particles that go at the same velocity. So even though the second class particle chooses uniformly, if you condition on the velocity that it chose, the next particle, or particles to its side, have some positive chance of actually choosing the same velocity. So they're not independent at all. And this kind of coalescence or convoy formation has something to do with the very interesting structure of these multi-species invariant measures, and the fact that you have some intermittency in these invariant measures, very gaps between and then clusters of these multi-species parts. Anyway, so that's something that unfortunately I won't go more into the proof of this, but I just wanted to mention as well. Okay, I think I should stop here. Thank you very much. Yeah, I can explain this picture a little bit more. So what you're imagining is that you start off with a sort of step function as the density profile of particles. So all particles and then no particles. And if you run that for time t, you have the Invisid-Burgers equation as the hydrodynamic equation for this model. And so what will happen is you'll still have a kind of a density 1 region. You'll have a linear rarefaction fan, and then you'll be flat again. So that linear rarefaction fan is being represented in the size of this fan. So in particular, you see at position minus 4,000, at time 4,000, you do have particles that kind of end up in that vicinity. So this is the leftmost edge of the rarefaction fan, and you have particles around positive 4,000. And if you plotted the density, so if you just took a line and you cut across at this time 4,000 and you plotted the histogram, the density of particles of the slope, you would find that it's uniform. Which is actually, so the general formulation is that if you take the derivative of the rarefaction fan, the slope and the rarefaction fan, that will give you the density of this process. So there are models for which you have more interesting Burgers equations. So for instance, for the stochastic 6-vertex model, you have a non-quadratic flux function, you have a non-linear rarefaction fan. And so you can, and this hasn't been done, but people are doing this, you can prove a similar phenomena, this speed process, this almost sure limit, and you get a non-uniform distribution over the rarefaction. Yes, I have some students. Oh, you can see the clustering perfectly. Yeah, I can. Let me see if I have a picture I can show you without. Well, okay, I can show you offline. My email doesn't pop up.
For the stationarity, to check this symmetry by permutation of alpha, we only need this just two gamma has the independent gamma, and we put a plus b and a plus b over a or something is again independent. So that is enough, or this property is not enough.
So you need, well, I don't think that one can generalize this to other polymer models. You can probably generalize this argument. I think this is something we're doing to other vertex models through a different mechanism than this infinity, but kind of a similar idea. But the two pieces that you need is you need the symmetry and you need to produce this renewal point. In the context of vertex models, the renewal point wouldn't be exactly the same nature. It will be something like a vertex that absorbs and produces infinite paths and kind of renews the path formulation in the vertex models.
Oh, okay, so that the infinity point is very important.
The infinity point is really vital for this. You can play games and try to produce multiple infinity points and say, well, okay, maybe this can allow you to produce more interesting invariant measures. And you see pretty quickly, but not that quickly, that it doesn't work to produce more invariant measures, but you can in fact produce invariant measures that are related not just to the single path polymers, but polymer hierarchies. So you can study polymer partition functions with multiple paths, and you can do this. There's a paper of Barakhan and Ledoux-Salvet in physics literature that starts to probe this.
And such property of this infinity can be found also continuous version, KPZ type.
So when you say continuous, you mean like the KPZ equation itself.
Yeah.
The general situation is that things are always easier when the more discrete they are. When you get to really continuous objects, it's sometimes hard to even make sense of. For instance, making sense of this symmetry is itself a challenge for the KPZ equation. You can do it, and what you get is you get a sort of symmetry between the KPZ equation with certain types of initial data and certain types of terminal data. And nobody's written down the proof of this. There's a little bit of work in proving that, but But if you prove that limit, in which you essentially preserve these bottom two rows as something discrete, and then you have the KPZ equation growth. And then you take the limit of this symmetry, and that will tell you that, well, it's the same as running the KPZ equation and then convolving with some terminal data. That's an identity that you can prove. And if you have that identity, then you can make the same argument work. But somehow it's like, well, why didn't you bother doing this if you already knew this from the log gamma? So I don't know a way directly for the KPZ equation to prove this identity any more than I do for this model.
Okay, so from online participants, it's okay. Or... Okay. So let's thank speaker again. Thank you very much.